Um, we currently have two more big topics left. One is about virtual memory, and another one is file systems. So I would be um, covering those two parts. So we'll have, as you might know, we'll start hybrid class from tomorrow. We created the polls and everything. So we give you instructions on how to join the hybrid classes, for where to go for physical class by end of today. The scheduled one is in Nalanda, but we'll confirm it once over Teams. Now, with that logistics out of way, let's talk about virtual memory. Now let's start with a small recap, right? So far, you have seen and learned about how memory management works in operating systems. And for operating systems, the everything that operating system does is to help or enable the programmer or the users. So for memory accesses, essentially we identified four possible things that most of the programmer wanted. The first one is that from a programmer's point of view, all of their memory addresses, like for their process, should start from 0, and that memory should be contiguous. That is, it will start from 0, go to 1, 2, 3, 4, and such. A memory should look to a program like just an array. And third one is that the process should be able to dynamically increase the memory whenever they need. Now, these first three requirements satisfied with paging. You learned about paging addresses, and essentially everything that paging does is meant to satisfy these three conditions. Now, the fourth condition, which is a more modern one, that is, uh, the programmer should have as much memory as they want. Now, we'll call it an illusion, because so far what we have seen is that whatever memory management or whatever you learned, everything was assuming that a computer has a main memory, have your RAM. You bought a 2 GB, 4 GB, 8 GB RAM, and everything, all the mechanisms that we talked so far, it's about accessing locations into that RAM. However, these days the programs and the processes might actually need much more memory than RAM. Can you give me an example like you everyday use, which will RAM than you generally need or generally have? Anything that you're using? Like any example of a program that you are using that games? Yeah, Vinith, absolutely. I was thinking about games. True. Like the bigger games can be 16 GB size, um, and 8 GB is quite common these days. Not many of us have 16 GB RAMs. Okay. Um, so the point is that you need to run games, and a more common one would be even your PowerPoint or your browser. Let's say, have you ever seen how much memory does a browser use? It's huge. If you keep, like me, 50 tabs open for a long time, a lot of processes are running and a lot of tabs are getting added and so on. So essentially, to do any modern stuff, this is a modern requirement. You cannot be bounded by how much RAM you can afford or you can even add on your computer. So that's how this whole concept of virtual memory came into being. That is, you need to have, or the OS should give you an illusion that you have as much memory as you want, and it might as well be more than RAM. So what is the idea of virtual memory? Like how to create this illusion? That is what we'll learn in this part. And this is one of the most beautiful part I feel in operating system, where by using smart usage of resources, you can give abstractions, illusions to the coder, which helped like rapid development. Now, what is the basic idea, like how to create this illusion? The idea is that, you are bounded by your physical RAM. It cannot increase. 2 GB is 2 GB, 4 GB is 4 GB. You cannot really create memory out of thin air. So the idea actually people came up with is that the operating system will stash away some pages from main memory, which is not used right now, and only resume them when needed by processes. So it's a little bit like, in your 16 GB game, you are not really using all the like 16 GB, the everything, like all the levels of the game at one point of time. You're just playing a small part of it. That means, I'm sorry, let me quit. Perfect. So essentially, you are only using a small part of it. So when you are not really using some pages or some parts of memory, some parts of program, you need to stash them away somewhere and then bring them back when needed. Essentially, then you might ask, obviously, we need a place to stash those pages which are not being used. So you need a large space where you can stash pages and then uh, put them back when needed. The natural choice for stashing pages and putting them back is your hard disk or SSD. The key idea is that all of the pages that is associated with your process is not really used at the same time. So what the OS would do, it would evict pages from main memory which are not needed. It will store and retrieve those pages from the hard disk or to the hard disk whenever the process wants. So in an ideal scenario, then your pages can be as large as your hard disk, essentially. So how does this actually work, like in operating system, like, stashing this and coming them back? We'll talk about them in very detail, like every single part of how this process works and how does operating system, what function they call, and so on and so forth. But here is a very basic diagram, okay? So say there is this virtual memory addresses that is available to a process. It starts from 0, it is contiguous page 0, page 1, page 2 to page, say, V. Each of these virtual pages will have to map to some physical location. That is done by this mapping is done by memory map. And what is the physical location? Previously, till the previous lecture, the physical location was only the physical memory. You take a page, you map it to a frame in that memory. But now with this new idea, now you can also have another actor, a storehouse sort of. This is your hard disk or your SSD, basically your storage device. It is also called a secondary storage. So when essentially a request for a page comes, the memory map will say that, we need to fetch that page. We need to give it to the process in this page 0, page 1, whatever is asked. So for some pages, it might be directly fetched from memory, the pages which are residing in memory at that given point of time. For some pages, it has to be fetched from disk to memory because that page is not in your RAM. So you need to take them out from the hard disk. And this process of bringing the pages from the hard disk or to the hard disk is called swapping. So whenever a request comes, either the page is in memory, which means that everything is good. If not, you need to get that page from disk. So now, any questions so far with this diagram? If not, I have a question. What is the advantage or issue with using hard disk as your storehouse? You keep some pages in main memory, you will keep the rest in your hard disk, and you bring them back whenever needed. That's an issue, great, yes, slow. What are some advantages? Let's start with advantages, because you see, like when people are doing this kind of stuff, they first wanted to get some features out of that. So Deep is absolutely correct, it is slow. However, it is slow, but still people are using it. Why? It is giving some advantage. Lots of space, yes, that's true. You are getting, that's the trade-off, you get lots of space, but it is slow. But let's see that what are the, like, let's actually say that this comment, lots of space, like when you are using this hard disk as your storehouse, how would the lots of space work? Essentially, what you create, you means you are the OS developer, you are the operating system and that runs on your logic, you create something called this virtual address space. A program will only see the virtual address space always. The virtual address space, as you have seen in the previous diagram, it will start from 0. There will be contiguous accesses, and the program will use it. Now, the program does not want to know and doesn't need to know whether those virtual address space, right, those addresses pages, they map to your main memory or to disk. The program doesn't care. The OS cares, but the program does not. So effectively, from a program's point of view, the virtual address space size is equal to physical memory size plus space allocated in your hard disk. Now here is something that is something called a swap space. So it's something that is interesting. You see what Deep was saying, lots of space, and I also told before that using this virtual address space idea, you can actually have your whole hard disk as your RAM to store your pages. So why does people have this space you allocated in HD, that is swap space? So what people generally do is to set aside a particular space in your hard drive. What people means the OS generally does is that it sets aside a space in your hard drive to store pages or retrieve pages. Why not? Why don't they use the whole hard drive? Any idea? I don't know whether you guys, so some of you might heard the term swap space, right? And you need to set the swap space in Linux while installing, like how much the swap space should be. So why don't people use in the hard drive, the whole hard drive as swap space? So Deep's comment was that, okay, getting there, but not quite that. Normal file system is not bad for storing pages. No, the page, I mean, if you think about it as a programmer's point of view, all of you are great coders, so or you know how to code. So pages are just like a structure, right? At the end of the day, when you implement, it can be supported by a file system, which will come later. So what else can be the reason that why soft space is only a subset of your hard drive? Any other ideas? To have faster access? Yeah. So Srijan mentioned that retrieval from sources is faster than from the normal HDD space. That is partially true. That is partially true. To have faster access, Rajat, yes, I mean, it is actually true. So you guys almost give all the pieces. So the point is that in swap space, you have a special file system for storing pages that actually makes getting the pages, retrieving the pages much easier. Ultimately, everything is a data structure stored on your disk, right? And you need to basically search which pages to get and whatnot. So there are a couple of more reasons actually. The reason is that, going back to Deep's comment that its hard disk is slow. So even if you actually assign say 512 GB of hard disk space, it won't really help you. Your program will stall and you have your program won't run essentially. So swap space is a fallback option. It gives you the illusion, but it's nowhere comparable to the speed with main memory. And another reason that you might not thought about these days, because hard disk is so cheap. Hard disk, I mean, you really wanted to buy 1 terabyte hard disk or 512 GB to actually store stuff that you feel are important, not to give it to OS for storing pages. There's something called swap partition, right? So when the operating system during installation, they actually set aside a swap partition that you cannot use for anything else, just for storing pages. And it is, essentially there are two reasons. One, swap space is faster because the OS needs to set aside a swap partition, have special data structure, special file system to actually get the data to memory, at least slightly faster. And you don't want your whole hard disk to be sacrificed for that reason. And even if you want to sacrifice, it won't really give you any speed up because hard disk is tremendously slower compared to a main memory. So with this knowledge that now virtual address space is your physical memory, the 4 GB or 8 GB RAM that you have, plus the swap space, let's actually see that how does the program sees the virtual address space. So now with this swapping idea, using this disk, the OS needs to do a lot of stuff that we learn, but the program does not need to know anything. It will use this logical address or virtual address space to store its instructions and data. In any kind of system, or at least the modern systems, generally for a process, they use this virtual address space. For each process, a virtual address space is assigned that you can actually access from page 0 to page n. And in that virtual address space, this is how the different parts are organized. First one is stack, and then that will go down, like grow downward. And second one is heap that will grow upward. So if it is like from page 0 to 1, 2, 3, 4, it is from 0 to 100, like 0 to max. Then your stack will go from max to downward, and heap will go from 0 to upward. This mechanism, this is basically a mechanism to increase or maximize the address space use, because this unused space, that is this here in blue, it's called a hole. And essentially, this hole is used by stack and heap to grow together. Remember that this is a virtual address space, meaning all of this is an illusion. And for this abstraction of stack grows downwards from max to 0, heap grows upward from 0 to max, 0, no one actually needs to assign any physical memory unless and until needed. If stack grows, a new page is needed, bring in a new page. If heap grows, a new page is needed, bring in a new page. So in this way, this stack and heap coexist and co-increase using the same virtual address space. Remember this diagram that stack always goes from max to 0 and heap always goes from 0 to max, because this is actually important in understanding, like actually coding some OS parameters about where to put data, what to put code in stack, if you have to design a real operating system for an embedded device. Now, this virtual address space have some specific interesting properties, or rather not properties, I would say. It will give you some specific, very interesting functionalities that you guys already used. We noted three functionalities of this abstraction of virtual address space. First, the system libraries can be shared across processes. This is all of you are using right now, okay? Because your system library, that is, the library of Windows, library of your Linux system, all of them are shared across processes. So how to do that? It is done using virtual address space. The two other things you guys actively coded with, one is implementation of shared memory, and the second one is implementation of fork. So let's actually see that how does this sharing works. Essentially, if you're using virtual memory, remember this whole stack, heap, data code, all of this part is just your virtual address space. That means this address space, like each page is mapped to some physical page somewhere. So that actually means no one is stopping the operating system to assign the same physical address, physical frame in the main memory or disk whatsoever in the physical location to the virtual location. Say here in process 1 is using a shared library. And the shared library can be and some dylib or glibc, something which is like fundamental for these processes to function. And that is given to you with Linux. So process 1's page, like process 1's virtual address space, will just point to the shared pages for these shared library pages. So in the virtual address space, the shared library part will point to a bunch of shared pages. Process 2 can also, the virtual address of process 2 can also point to that shared pages or map to the shared pages. It's just pointer manipulation ultimately. And the shared pages will contain your shared library. So virtual address space enable sharing of the same data and code across programs. This essentially have a more involved application that you used in fork. So what fork does? Fork essentially create a child from a parent. Now you see, like if you are running a parent process in your main and so on, before calling fork, the parent might have a virtual address space, a lot of stuff in there. When you call child process, when you call fork, a child process is created, which is an exact copy of parent. Copying is expensive. Think about it, like all the pages, like hundreds, thousands of pages, like memory pages that needs to be copied fully to create the child. That means forks needs to be expensive now. For that, to actually reduce the expense, there is an optimization based on this virtual address space idea that virtual address can actually, multiple virtual address can map to a physical address. Using this idea, there is something called copy on write or COW or COW. What is copy on write? Copy on write is a mechanism which allows both parent and child process to initially share the same pages in memory. The child process point out to the physical locations which the parent process shares. If either of these processes, like either child or parent, changes the element, the content of a shared page, then the shared page will be copied to a new location. So this is called vfork, or basically virtual. V stands for virtual here. You're using the power of virtual address space. And this vfork system call does exactly the same. So you have a parent process. The parent process calls fork. And when the child process is created, in the PCB of the child process, all those virtual address space will point to the same physical address space as the parent. Whenever the parent will change any of those physical address space, like write or parent or child process, either process, will try to change the data in that physical address space, only then that page will be copied and the changes will be written. Diagrammatically, that means that say you have a process 1, the parent process 2, the child process. So in physical memory, process 1, the parent process, will point to page A, B, C. And once the child process is created, the virtual address of this child process, they will also point to the same page A, B, and C. Now, if the parent process or the child process, in this case the parent process, modifies the page C, immediately there will be a copy of page C, and the new page will be pointed. This pointer will be, this virtual address space will point to this new modified page C. So this is the basic idea of vfork, and it is extremely fast because, as you can see here, if you have used the whole copy, like if you don't use copy on write, so copying something only when copying the pages, only when the pages are changed or it is written, you would have to copy page A, B, and C. Now you just need to copy the page C. You already have a 3 times performance improvement. The performance improvement will be higher, basically higher and higher, if this parent and child process is not modifying a lot of pages. Questions so far? Okay, so to recap, essentially we introduce the virtual address space for a process. The virtual address space will map to some memory location, main memory, disk memory, the process doesn't care. A virtual address space is just there. And the advantage, the virtual address space is organized as the stack grows down from max to 0, heap grows up from 0 to max. After vfork, how is the parent awaked? What do you mean by awaked? These are two different processes.
So you mentioned that vfork suspends the parent process, right? So does the parent ever resume, or how is the parent resumed?
Yes. So essentially, the parent doesn't. So vfork system call has the parent doesn't. So once the vfork is done, the parent wakes up and start its own whatever it's want to do. It doesn't really. How is the parent process awake? It's part of the vfork, essentially. It schedule the process.
So why is it different? How is vfork different from fork?
Yeah. So vfork in fork, if you are using fork, then that is what I wanted to say. Basically, in vfork, if you are using fork, then page A, so the process 1 will point to first page A, page B, page C. After fork, the process 2 will have page A1, page B2, A1, page B1, page C1. And page A will be copied to page A1, page B to copy page B1, and page C to copy page C1. If you're using vfork, then all of this virtual address space will map to the same physical address space. And it will only be copied when either parent or child, after it wake up and start running and all these things, if change any of these processes, any of these pages. So vfork uses this virtual, so vfork is different from fork by using the copy on write mechanism. You don't really copy.
So sir, yeah. So sir, we should, like when you're writing a shell, we should always use vfork and not fork, because.
Yeah, there we go.
Okay, got it.
Copy on write is a very, very powerful mechanism. You will know that more if you are at stage systems and do more advanced stuff. Copy on write just means that, unless and until something is changed, some pages or some data structure is written, You will just do pointer manipulation. You will never copy it. Copy is expensive. Okay, cool. So virtual address space, great. It actually encompasses both memory and disk, and it actually allows you to make the fork even faster by the sharing of pages. Now, I'm sorry. Now, these are the advantages of this mechanism, virtual address space, right? And combining disks and physical memory. What is the issue? Deep already answered the issue, or at least give the hint towards it. While using any issue like with hard disk is our storehouse, is that the virtual address space, if it maps to your RAM, fast. If it maps to your hard disk, slow. Any idea how slow it is? Give me a wild estimate. You can Google, or you might not want to. Just give me an estimate. Like how faster are the accesses, read and write access, is for main memory compared to your hard drive? 100,000 times. Okay. Anyone else? Million times slower than RAM. Okay. Anyone? Anything like it's a really huge estimate. It's not that much. However, it is around 50 to 200 times slower if you are considering hard drives. If you're considering SSDs, even, you can have some SSDs in your machine. Any idea how slower it will be? How slower will the hard drive will be compared to your RAM? You guys should know, right? I mean, that is what decide whether you will buy a hard drive or SSD or whatnot. Any idea how slow is an SSD compared to your RAM? It is slow, by the way. But any estimate? Yeah, Shanda is correct, and Deep is also correct. So 10 to 30 times. Now, it doesn't really look too much to you, right? 50 to 200 times. It's not 100,000 million times. No, no, no. It's a 50 to 200. But imagine this. When you are booting your system, how long will it take? It will take around 20-30 seconds minimum, 1 minute, 2 minutes, 1 minute maximum. More than that, you have a problem. But previously, it took 1 minute to boot up your system, put everything into memory. If you're using only hard disk and no memory, it will take 50 to 200 minutes. You switch on your computer, it will wake up after like what, 1 hour to 2-3 hours. So essentially, the main issue is that the hard drive is extremely slow. So virtual address space gives you this awesome capability of increasing your memory without spending anything. You are already have a hard drive, just augment it to the memory. The problem is that it is extremely slow. And as operating system developers, you need to make it faster by some way, somehow, by using optimization systems and so on and so forth. And we'll talk about it. So the challenge, right, for operating system is that, so now you know about virtual address space and all these things, but for the operating system, and the virtual address space is for programmers. But the challenge to operating system is that how would the operating system that you wrote will utilize this larger but slower hard disk device to transparently provide user the illusion of a large virtual address space. What does transparently means? Essentially, there are two angles of transparency. First one is programmer angle. You don't need to know where your virtual address is going. It might be on memory. It might be on hard disk. Why would you care? But the second part of transparency is that if you know that sometimes your program takes 2 seconds to run, sometimes it takes 2 hours to run, that's not really transparent, is it? It might take 2 seconds to run your program because all the pages are mapped to main memory. On the other hand, if all the pages are mapped to your hard drive and you are not really doing the smart things that we learn, then it will take the same code, everything same. It will take you like 200 times more. That is unacceptable. So how to solve this challenge? That is the question that actually plagued West developers for 90s and 2000s quite a bit. And they identified, I would say, 3 primary domains to look into and optimize. What are the domains? There are 3 requirements for making this whole experience to the programmer transparent. The first one is the first one is that given the operating system and the computers in general use processes that stores and retrieves data primarily from main memory. So the first requirement is that you need to incorporate swapping in your virtual to physical address space mapping so that transparently you can load and store pages from disk. How to do that? What is the process of doing that? Incorporating the swapping to and from disk in your lookup from virtual to physical address space. The second requirement is that determine that what pages do you need to swap in or out smartly. Because if you're swapping in a lot page so swapping in like you're reading from disk and putting to memory a lot of pages, that is expensive. If you're putting a lot of pages to memory, it is also expensive. Disk is expensive. So how to determine which page to swap so that the disk access is minimized? That's the second requirement. The third requirement is that now that you have used disk to actually put some pages from main memory to there and free up space, how to allocate that freed up space to processes. You cannot really do it, whatever process wants, you just give it to them. You cannot do that. Because then you actually, freeing up frames is expensive. Freeing up main memory is expensive. You need to get something from main memory, the data, and put it into hard drive. Expensive. So you need to also be smart about who you're giving the free frames and how you will give them. For the rest of this virtual memory, we'll talk about how does people solve these problems using their smarts and quite a bit of algorithm knowledge. So questions so far? Okay, then. So let's actually see that how to, let's actually try to, first understand how can we incorporate the swapping from and to disk space in your logical to physical address mapping paradigm. We generally used, or generally people use something called demand paging for that, for this efficient swapping. What is demand paging? So one way of actually swapping in or basically bringing the pages into main memory is that whenever a process starts working, say your game, you could bring the entire process, all the data in memory at load time. However, if it is your game, which is 8 GB size, you might not be able to do that. And also, this is expensive. Even if it's not a game, it's only 50 MB of software. It's expensive. You have to read 50 MB from your hard drive, put it into main memory. So to that end, people come up with this idea of demand paging. The idea is extremely simple. Bring in, like you only have your unit of bringing in pages or bringing in data from hard drive to memory is always pages. So bring in a page into memory from hard drive only when it is needed. Needed by whom? Needed by the process. The process asks, we'll give it to them. But we won't proactively bring in the whole, everything the process had, the 50 MB of software into the memory at runtime, like at that very beginning. The demand paging has multiple advantages. Of course, less I/O needed because now instead of reading 50 MB, you're reading only 5 KB. Huge improvement. And essentially, you are cutting down the unnecessary input output. Like here, I/O essentially means disk read and write. Of course, you will also need less memory. But why less memory? Simply because you're only giving the process a space in physical memory, the RAM, the one that they need at that point of time. So less memory will be needed. The response will be faster, of course, because the disk read and write decreased. And clearly, you can incorporate more users because previously one process was eating 50 MB of your RAM. Now it is only you are only giving them 5 KB. So essentially for implementing this demand paging means the process demands, you will give them the page. Doesn't demand, you won't give them any page. So for this demand paging, you need to swap the pages. And this is how the swap works, right? So if you have a program A and program B, essentially program A has their virtual address of this program A maps to this physical memory space. Essentially, the program B needs, during demand paging, program B needs some specific data like this 3 pages, and the OS will bring those pages into memory. And at the same time, program A doesn't need these pages, for example. It is not using it at that point of time. So it will the OS will swap out. How to know whether program A is using or not? We'll talk about it in detail. There are heuristics. There are mechanisms, rules to actually determine smartly if program A needs it or not, like which pages to swap out. But essentially, the idea is that in demand paging, you need to swap in some pages when necessary and swap out when unnecessary. Demand paging, like at its core, mostly talk about which pages to swap in, and the answer is that whatever program B needs. So how does that work? Say program B is asking like I need page I or page P, and say like give a page number. If that is an invalid page number, then the OS will say, sorry, you don't have permission to access it, abort. However, if that page is not in memory, then it will then the OS will bring it to memory. If it is in memory, then process B has no problem. It will just continue as it is. In today's operating system, this swapping, right, this not in memory, bring it to memory, that is done using a lazy swapper. It never swaps a page into memory unless page will be needed. It won't proactively get all the pages or 2, 3, 4 pages for B to from disk to memory. Why? Because disk is slower. There is another name of a swapper that deals with this swapping of in and out of pages, which is called a pager. Remember that this is actually an interesting point. So why do the swapper has given a new name called pager? Any idea? So whatever process of whatever part of OS is swapping pages from memory to your hard drive, it's called a pager because it deals with pages. Why a new name? Any idea? Hello? Am I audible?
Yes, sir.
Okay. So if you don't have any idea, then let me give you a hint. Swapping generally means to swap something completely in traditional sense. Swapping a whole process, the whole memory from all the data of a process, all the instruction of a process from memory to disk. That is what swapping traditionally means. But in our case, in the modern sense, swapping primarily means swapping pages. That's what it was given a new name, pager. But in other paradigms like embedded systems and so on, if you say I am swapping a process, you are putting everything of that process into disk. So when we say swapper in this lecture and in this course, we'll primarily mean a pager. So how should the pager work in demand paging? Essentially, this pager brings in only the pages which are required into main memory. And to do that, sometimes the pager needs to free up some space from main memory and it will evict some pages. Which pages should the pager bring in and which page should the pager bring out? We'll talk about in requirement 2 and partially requirement 3, actually requirement 2 primarily. So the pager needs to actually determine, right, what pages to bring in and what pages to go out. Now, assuming that the pager knows which pages to bring in and which pages to bring out, if a process asks the pager, give me this particular page, and if that, then the pager will first check whether the page is already in memory, like in primary memory, or in other terms, memory resident. In that case, it will just go ahead and do nothing essentially because the page is already in memory. The pager will just, there is no need to swap. The pager will not do anything, just return. So there is no difference if a page is in main memory already. There is no difference between a non-demand paging scenario and a demand paging scenario. Pager won't do anything. It will just return. However, if the page that the process A asked and which is not memory resident, which is not in main memory, then you need to fetch it from disk. The key constraint that you have is that you cannot change program behavior to do that. What is program behavior? Because the program behavior is something written by the software, like the developer, and the developer does not really know that whatever is in main memory, whatever is in disk. So you cannot really ask the programmer to change their code because and only ask for pages which are in main memory. You cannot. So the pager needs to provide that abstraction to the developer that, okay, you just gave me a virtual address and I will give you the required data, the page. Essentially, to incorporate, to achieve this feat, the pager would need two new machineries. Okay, one is called a valid invalid bit, and another is called a page fault handler. So these two new machineries will enable our pager to transparently provide the pages to the process, whatever pages the process asked, without the process doesn't need to worry whether the page is actually in main memory or in disk. So what is a valid invalid bit that helps the pager? Essentially, with every page table entry, a valid or invalid bit is associated in today's operating system. And essentially, the invalid bit has two values, V and I. V essentially means that it is in memory. The page is in memory. I, it means it is not in memory. Initially, when a process starts executing, the valid invalid bit will be set to all invalid, because when the process starts, remember, in demand paging scenario, nothing is in memory. Everything has to be fetched from disk whenever the process asks. So initially, it is set to invalid for all entries for a process. it will look as something like that. Like while executing the process, some of the pages, it will be the valid variable v, right, which is valid, meaning what only means that page that the process asked in their virtual address space is in memory. And sometimes it will be I, meaning the process that the page that the process asked is not in memory. And during this particular, like whenever this valid, the operating system, whenever it checks the valid invalid bit and found an invalid page, it will raise something called a page fault. So how does this page table will look essentially whenever with this valid invalid bit? You see, it's here is an example, the last one for the day. Essentially, here is your virtual address space, logical address space, like 0, 1, 2. So there are 8 pages. In the page table, for many of them, essentially the valid invalid bit is v. Precisely for 3 of them. Those 3, essentially, when we say that valid invalid bit is v, that actually means that those 3 are already in memory, like A, C, and F are in memory. Whenever in page table entry, a particular value, like for example, here the 1 is in B, the 1, the virtual address 1 maps to something called this, there is valid invalid bit for virtual address 1 is I. That means B is not in memory, but in disk. So if I want to access the virtual address 1, it will raise some, it will check it means the OS. The programmer will ask your OS that give me this virtual address 1. The OS will go to the page table, see there is an I, meaning it's an invalid bit, meaning that page is not in memory, but in disk. What would the OS do? It will raise something called the page fault. We'll stop today here, and from the next class, we'll say that how the page fault is handled, how the page fault will occur. What will happen after you get page fault. Okay, we'll stop it here today. So questions? Okay. If there are no more questions, let me. Okay. Okay then. Just see you tomorrow. Can it happen that the page is not in the hard disk as well? Yes, it can happen, Jessica. That's a great question. So remember, so essentially I very briefly mentioned that if it is an invalid reference to a page. So the invalid reference essentially means that page does not belong to the virtual address space. No such page ever existed. Even in the page table entry, there is no entry of that page, either with V or I. Then the OS will just raise an exception and say, like, we have a. It will just abort, generally throwing a segmentation fault or invalid memory access. Any other question? Yeah. Go ahead. Okay.
Okay, Meenak, Shaptoshi here.
Yes.
Yeah, so just I wanted, I mean, now that technical part is over. I just wanted to ask the students. So it seems that you have got a mail about end semester exams. Uh, what exactly have you been told? Can anyone say?
I'm stopping the recording in the meantime.
Yeah, sure.